And on behalf of the entire staff, I'd like to thank you for coming out today to join us in the opening of our new exhibit on Ames Laboratory. We're really excited about having the exhibit here. I want to introduce at this time our Deputy Manager of the Albuquerque Operations Office of the U.S. Department of Energy, Mr. Ron Cochran.
Thank you, Joni. And I'd like to also welcome all of you here for this very important event. It's really quite a pleasure and an honor for me to have the opportunity to come here to introduce two very distinguished people in this field. Most of you probably don't know, but by training, I'm a metallurgical engineer, and these are some of the guys who did the work that got many of us interested in metallurgical areas some years ago, and I sort of followed through that working at DuPont, Savannah River, Oak Ridge, Hanford, and other places. So it's really quite an honor for me to meet these gentlemen and to introduce them to you. Now, the work that was done by Ames Laboratory for the Manhattan Project is very, very important work. It has not in the past gotten quite the publicity of some of the other activities at perhaps Los Alamos, Chicago, Oak Ridge, places like that, but it was an absolutely vital element in being able to successfully build the atomic weapons at that time. Now, we want to take this opportunity to try to provide a little better spotlight on those activities at Ames because they were very, very, very important. So today we're going to celebrate the opening of this exhibit to focus attention on the work of Ames Laboratory. Now, in order for the work of the other laboratories to proceed, many tons of very high purity uranium metal were required. Until the process was discovered at Ames to produce this metal, only gram quantities were available. But by 1942, Dr. Wilhelm and his team had produced over 4,000 pounds of uranium, tremendous amount in such a short time. And this was the largest single source of uranium for the CP1 reactor in Chicago. By 1945, in fact by August 45, 2 million pounds of uranium metal had been produced at Ames. Now, Dr. Wilhelm is with us today, and he will discuss the development of the processes for large-scale production of uranium metal. His experimental abilities, his persistence, and his innovative metallurgical capabilities have led to many important scientific advancements in this area. He's the co-inventor of the process which supplied uranium metal to the Manhattan Project, and his research on metals has led to 44 inventions related to atomic energy. Dr. Wilhelm served as the first associate director of Ames Lab, and he served there from its inception in 1947 until his retirement in 1966. Now, at Ames Lab, just looking at it from an institutional standpoint, a world-renowned research center grew out of the Ames project. And that laboratory, which is operated by the Iowa State University for the Department of Energy, is one of the 12 Department of Energy multipurpose laboratories. And they are contributing in many ways to solving problems that are important to this nation. The laboratory's major research effort, the laboratory at Ames, is in the physical sciences. But they have placed particular emphasis on preparing new materials whose chemical properties are characterized, evaluated, and interpreted at the laboratory. So without any further words, let me introduce Dr. Wilhelm. Thank you very much.
Thank you, Ron. As I look back about 40-some years, I recall an announcement coming over the radio that there was going to be a very important announcement from the Department, well, it's called the Department of Defense now, but then it was the Secretary of War back in those days, and that everyone should have their radios tuned in to get the announcement. This was about August the 7th of 1945. Well, I called the wife, and I thought maybe there might be something coming up of interest, and she could find out maybe what I was working on. And so we all got tuned in, and sure enough, Secretary of War Stimson came on and began to tell about the first atomic bomb that had been dropped on Japan, and reconnaissance had flown over the area and evaluated it, and everything was a success. Now, in his talk, he gave credit to 4 educational institutions in the United States that made notable contributions to the atomic energy program. Those 4 institutions were Columbia University, University of Chicago, University of California, and Iowa State College. Now, a lot of people kind of wonder why Cal College, as we were referred to most of the time, was an agricultural university, or college at that time. And where in the world would they get into this atomic energy business? Well, I'll have to tell you a little background so we can see why we were mentioned by Secretary of War Stimson. I have to go back when I went to Iowa State University as a graduate assistant in the chemistry department. This was the fall of 1927. And I was going to major in physical chemistry. The research in physical chemistry was under the professor of physical chemistry, and his major research was in applied physical chemistry, applied in the area of metallurgy. Now that was a kind of an unusual area for a chemist to be working in. Well, as time went on, I got a doctor's degree, but my doctor's degree was in the area of spectrochemistry, because the person who was doing the research in metallurgy, the professor and head of physical chemistry then, got a job in industry. It paid him a lot more than teaching did. His job came out of his research in metallurgy. And he took a job as director of research for a steel company, Armco Iron Steel. He left in January 28, just after the first quarter that I had with him, studying metallurgy, and along with inorganic chemistry and organic chemistry and physical chemistry. And the position was turned over to one of his students who had just gotten his degree. And I had a job then teaching metallurgy to mechanical engineers, and I also taught undergraduate physical chemists. And I had worked on a course for ceramic engineers to learn more about the ceramic systems. And I also had worked on a course in spectrochemistry for graduate students in chemistry and seniors in chemistry. So in 1937, when this former graduate of Dr. Hayes, he got a degree, or he got a position with Western Electric as a metallurgist, Western Electric in Chicago. And this is in February of '37. And when I came over to teach a junior course, the head of chemistry met me at the front door and says, "You're going to teach graduate thermodynamics this morning." Well, I hadn't looked at old Lewis and Randall for 7 years. And I'd forgotten quite a bit of what LDH bar and all that stuff meant. So, well, I met with the class. Fortunately, they had problems to sign, so I let them work on the board. But I couldn't understand the problems. I said, "You folks sign yourself some problems for next time, and I'll sleep on that old book of mine, and I'll finally catch up with you maybe." Well, I caught up in a week or so. So my school teaching schedule had been shifted around a little bit. Anyway, things went on the rest of that year. And then in September of '37, Dr. Spedding came to head up physical chemistry. See, I was just an instructor, and I had gotten my degree at Iowa State, and the president there, he didn't want any inbreeding at all. He wanted to get new people in, so he got Dr. Spedding. So I still had a job, and this is through the Depression, you see. Glad to have a job then, even though it didn't pay very much, but it was a job you could live on. Anyway, Dr. Spedding came in September of '37, and I was doing research in spectrochemistry and research in metallurgy at that time. Well, he was not interested at all in metallurgy. He thought the metallurgy research ought to be done over in engineering. So he turned that all over to me, and then I shared my spectrograph with Dr. Spedding. He was interested in rare earth absorption spectra and spectra associated with the inner electron levels of the rare earth metals, rare earth elements. Well, we went along together, and I always did a little bit of consulting work because that seemed to pay off. The work that I did in spectrochemistry, the thesis work was dealing with band spectra, molecular spectra, very interesting work. In which you can actually see, say, a diatomic molecule when its electronic levels change, when it shifts from one level to another and so on. You can see that, and you can see the vibration between the two atoms of a diatomic molecule in the gaseous state. And if you had fine enough resolution, you could get the rotational energy changes too. Very interesting, but I didn't know of anyone that really needed that so I could do any consulting work. I had to make a little money on the side. I did consulting on hog tonics and antifreeze and most anything they wanted to pay me for, but they didn't need any of this molecular spectra in it. Well, anyway, we went along teaching together until 1940. I did some consulting work for Burgess Industries, and the Burgess Industries, this is during the summertime in 1940, and they offered me a job at more salary than I was getting there at Iowa State. It didn't have to be very big. Well, you wouldn't believe it, I tell you what the salaries were, but anyway, they gave me a letter, what they were going to pay me, and so I brought it back. I'd been over to the company, and they gave me the letter, and it was over at Freeport, Illinois, and brought it back and showed it to Professor Coover, who was head of chemistry. And he read it, and he says, "Are you going to take it?" Well, I said, "I'm going to take it unless you want to keep me here." Well, you see, I had him in sort of a bind then, I think, because nobody else was ready to teach that undergraduate course in metallurgy to the mechanical engineers. Nobody was ready to teach this course in spectrochemistry that I was teaching. and nobody ready to teach that course to the ceramic engineers. Well, he says, give me a little time. So I waited a while, and the company in Freeport kind of breathing down my neck and said, when you go to decide to accept? Well, I went back to Cooper, and he put a little more pressure on the president. You see, the president then was Dr. Friley, and he followed the same idea that the earlier president had developed, no inbreeding. I'd be inbreeding. But Cooper was such a jam, I guess, that he got Friley to, okay, make him a assistant professor. Well, that broke the water there, you see, because if I'm there for 3 more years, I get tenancy. Well, anyway, that was in 1940. And I had my first graduate student in 1941 in metallurgy. And he'd gone out into industry. Then he later came back to Iowa State, and I let him work in the uranium production plant a while, and then he took a job down at Los Alamos. Well, how we got into the atomic energy work was in this way. There were 2 parts to the atomic energy area. One involved the isotope of uranium, uranium-235, and the other one involved the conversion of uranium-238 over to plutonium. And either U-235 or plutonium would serve for atomic power. Early we were thinking mainly of atomic power to drive ships and so on, but we soon converted over to, became the atomic bomb was the major objective. Well, Spedding got into this because Compton was head of the plutonium project at the University of Chicago. And Spedding, Compton and Seaborg, who was the person to furnish the first plutonium at the University of California, and he and Compton, as well as some others, had set the system up. And they figured they needed a rare earth chemist, but a lot of the fission products were rare earths. And also, these physicists knew that uranium did not belong in the same family with chromium, molybdenum, and tungsten. See, it was right in the old chem tables, periodic table. Uranium came right below tungsten. Now, chromium makes good steel. Chromium steels, and molybdenum makes a little better steels. Tungsten makes some real good high-speed steels. Boy, uranium ought to be a wonder. And it fell flat. We didn't know why. In chemistry, it was in that family, but it didn't do anything. You could make cigarette lighters out of this flints, out of this metal, with uranium, with iron, uranium and iron. But anyway, they knew that there was another series similar to the rare earth series. The rare earth series of elements are called lanthanides. Well, up here at the heavy end of the periodic table was actinium, and everything beyond that were rare earth type elements. They called them actinides. Well, anyway, so Spedding was the only person they could think of that might be able to help them with the chemistry. So he was called into Chicago, consulted with Compton, Arthur Holly Compton, and he was to take over the chemistry at the University of Chicago, chemistry laboratory of the plutonium project, and was also named the metallurgical laboratory at the University of Chicago. But it was also called the plutonium project. Well, it didn't take Spedding long to find out what some of the problems were, and he found that the University of Chicago planned to set up a metallurgical laboratory to study uranium and its compounds, metal compounds. And he had visited producers of uranium metal at that time. He and other fellows associated with him visited metal hydrides, which is producing uranium metal by mixing calcium hydride with uranium oxide, centering that up and getting a powder uranium with calcium oxide mixed in it, and then they had to leach it out and press this powdered material into a little pack, about like yeast cakes used to be. You buy yeast cakes at the store. People ate those things for health, as well as using them for baking bread. Anyway, that's what these little compacts look like. Metal had never been melted. Now, but they were producing in ounce quantities, and over at this was at Beverly, Massachusetts. This process came out of MIT when Peter Alexander was a student there. He took it down to Beverly, Massachusetts and set it up as a production plant. The other process was by Westinghouse at Bloomfield, New Jersey, and it was a fused salt electrolysis of a uranium compound. They made their own uranium compound, which is KUF5, a double salt of potassium fluoride and uranium tetrafluoride, and then this was put in a sodium and calcium chloride solution and in a graphite crucible and electrolyzed onto, uranium was electrolyzed onto molybdenum electrode. And then that was pulled out of the salt bath and cooled a little bit and dipped back in to get a salt coating on it, and then it was put in a big drum and leached and so on. And the powder was taken out and pressed into compacts and then put in a beryllium oxide crucible in a vacuum in a echo induction furnace, and then it was melted down into little cubes or little half moons and so on. Anyway, that was the production process that Compton ran onto. That was a gram quantity process. But Compton thought he'd probably have to have some compounds like carbide studied and nitride studied and others. You might not be able to get the tons and tons of uranium metal that they envisioned would be needed. He had assigned another university in the East to look into all metal production and try to design some process to get these tons of uranium metal. Well, Spedding knew about this, and he says to Compton, he says, now, you don't have your laboratory ready. You've ordered furnaces for it, but it'll be a while before they get here. And we have a laboratory out at Ames and personnel that can go to work right away on this, on problems you have in metallurgy. Well, Compton thought a little bit, and he says, that's a good idea. He says, you start up, and when we get our laboratory ready, you transfer all your personnel to Chicago. Well, we went right to work then, making uranium carbide, and tried to make, I'd investigated these two plants, and another person was working on uranium metal production by a process that had been developed back in 1926 at the University of New Hampshire. And this fellow, I knew the fellows that worked there. He'd gone to the University of New Hampshire. He was at the Bureau of Standards. And he's working on a process to make uranium from uranium tetrachloride. Now, uranium tetrachloride is a messy thing, but it's hygroscopic and so on. So we didn't want to get into those processes. So we went through the literature to see what else had been used. Well, carbon had been used by Moissan years ago. So we could get uranium metal by just heating up the oxide with the proper amount of carbon, but we always ended up with a little carbon in the metal, and it was always brittle. But we could get uranium that way. So we were wondering what halide could we put with the uranium to do a similar reduction like the fellows did at the University of New Hampshire. Well, about that time, Compton was making compacts of sintered oxide and and also the carbide, which is put in his test reactor under Stagg Field, trying to decide what's he going to put in there. Wasn't going to be able to get metal, he thought. Well, we made a lot of carbide for him, a lot of sintered oxide. And they were looking for the compound like carbon and oxygen to have very little neutron capture. Fluorine was one of those elements that didn't have, and they could make a tetrafluoride. Johns Hopkins had worked out a process for making uranium tetrafluoride. So they turned that process over to a company in Cleveland, and Harshaw Chemical it was. And Harshaw Chemical stepped up the uranium tetrafluoride process, and Spedding got a hold of one of those little compacts, a little cylinder about 2 inches high and maybe an inch and a quarter in diameter, and brought it out to the Ames laboratory. Now, I started in with Spedding when they first announced that we were going to go into this work. I joined in about the 21st of February in 1942, and we took on 2 graduate students at that time. And then the next month, I had another fellow to finish his PhD, so I added him into the group. And then there was a fellow from out teaching that had known Dr. Spedding, and I had him come in. He was Wayne Keller, and my fellow had just gotten a degree was C.F. Gray. Well, these fellows, along with Adrian Daney, the graduate student, and Ray Hoxing, the graduate student, went to work in the laboratory for making these compounds and so on. One fellow was, like Ray Hoxing, was trying to find out how to protect uranium from the elements. It's pretty reactive, but when it gets hot, it needs protection. It'll burn up, it can catch fire. Well, anyway, it was a problem on how to melt and cast uranium, especially if we're going to get tons of it. You've got to have more than a little beryllia crucible, like Westinghouse used. Beryllia was tanned all right, but fortunately we didn't use it for 2 or 3 reasons. One, it was really high priced. The other, we found out later, is quite toxic. Berilliosis was one that you might get involved with. Anyway, C.F. Gray went to work on with me on the casting problem, and Wayne Keller worked with me on the metal preparation plan. Well, when Spedding brought that, I better say that Gray had the casting problem solved before July 1st. Found that if you controlled your temperature well, you could melt and cast uranium in ordinary graphite. And graphite crucibles could be made from large graphite electrodes that were made. You could get them up 12 inches in diameter, and I think probably we could have gone to 24 inches in diameter. You just hollow the thing out, you've got a crucible. So we had the problem for melting tons of uranium metal and casting it by July. We didn't have the tons to melt. I was still working with gram quantities from Westinghouse. But Spedding brought back this little piece of UF4, green, it's green in color, called green salt, uranium tetrafluoride. And Keller and I ground up part of it. There's still a piece of it somewhere. I can't locate it right now. A piece of that little cylinder. Anyway, we ground it up and mixed it with calcium, granular calcium, and put it in an iron bomb. It had a little liner in it. We learned how to insert liners out of refractory powders, like magnesium oxide. Anyway, and a fuse wire inside sealed the thing up. And on August 5th, 1942, we got our first ingot of uranium metal. Nice little ingot out of it. Of course, it was a small-scale operation, of course, only an ounce or two of metal that was produced, but it worked. Well, then reported that, and we used calcium, so I wrote a report to Spedding on August 5th, 1942, that we had in mind, and we got enough material to test magnesium as a reductant, and maybe sodium and possibly aluminum as a reductant, because calcium wasn't too available right then. Fortunately, the Electromet company had set up a plant and was about to get it in operation up on Sault Ste. Marie, Michigan. Previous to that, all calcium that they used came from France, and during the war it was difficult to get anything over from France. So they set up their own plant for calcium. That calcium became available later for expanding our operation. And Rodden, who was working on the chloride, uranium chloride reduction with calcium, had found that the calcium, early calcium, had a high content of boron, and they had worked that out with the metal hydrides company, and so we could get very pure calcium then at that time, but it didn't have great amounts of it, not enough to look forward to big tonnage. Well, I think it was on September 24th, 1942, by that time we'd made enough reductions of uranium tetrafluoride by the bomb process that Kelly and I worked out to cast a fairly large ingot, large on that date. We had, so Gray and I melted up these various reductions that Keller furnished, and we cast our first ingot. It weighed 11 pounds. And that's 5 kilograms. And I took that into Compton. Spedding was in Chicago at the time. I took it into Spedding, rather, and he and I went up to Compton's office, and Compton looked at that. He'd never seen so much uranium in one piece, and of course he doubted that it was solid inside. Busy being a physicist, he couldn't believe it. And that, of course, the metal, or just if you allowed it to cool a proper way or a certain way, it would have a pipe inside. Compton didn't know what to call that pipe, and so he called it a void or a hole or something like that. But he says, take it over to the biology department. They've got a shop for us in the basement, and you crop that and cut the rest of the thing in two, and we'll look at it and examine it and evaluate it. So I went over there, and they had a milling cutter, just a milling saw, a milling machine that has a saw blade, and this fellow crapped off about 1/4 of an inch at the top. Sound in there, wasn't a bit of a hole. Cut it halfway in two, about 5 pounds each, the 2 pieces. And I took the 3 pieces then over to Compton. He gave one of them to Ed Kreutz. Ed Kreutz is one of the fellows from Princeton. He'd come in, and he measured the density of it. And density was about the same as gold, something like 19.04 grams per cubic centimeter. The other piece went to the chemist, I think a fellow by the name of Charles Coriel. memory serves me properly. He took the other piece. I don't know what he did with it, but a day or so later, after I'd gotten back, this is the 24th of September, I'd gotten back a day or so later, Richard Doane, who was Compton's right-hand man and also a director of the metallurgical laboratory. See, Compton was director of the plutonium project, but Doane was director of the metallurgical laboratory there at Chicago. But anyway, Doane came out to Iowa State and sat down with me and Keller, and he wanted to know all this and that about it and what we thought about doing some more. And right away he says, okay, you fellas set up the plant out here, pilot plant out here, and get going in your production. And forget about going to Chicago. So there, the Ames laboratory was established. We never got to Chicago. We continued on. And we worked with calcium reduction clear up through December. And by December 2nd, of course, we had 2 tons produced there in the chemistry laboratories. 2 tons of this metal that we made. And by January of '43, we were using magnesium, which is much cheaper. Didn't take as much of it, has much greater purity. Calcium, you see, is 40, it took 80 grams of calcium at least stoichiometrically to reduce 238 grams of uranium. But it only took 48, I believe, something like that, well, something in that neighborhood to do the same job with magnesium. And magnesium was cheaper and greater purity. So we were on our way then, production, and that's how Ames Lab got established. And then after the war, of course, everything was super secret then. It was so secret that we were not let anybody know that we had a secret project. And after the war was over, Leslie Groves, general from the Manhattan, the Manhattan engineers, Army engineers, they took over completely with the project in 1940, about March of '43. They were in completely. Before that, we'd operated under the NDRC, National Defense Research Committee, and Doane had set us up with $25,000 contract right there from the time he visited us, so we get going in production. And later on, the OSRD came in and established some other operations at Ames. Mostly that was research. And well, as soon as I was assured that we were going to have to set up a plant there at Ames, I looked around for a building. The chemistry building wasn't very well set up for production, especially tonnage quantities. And I found an old brick building that had been abandoned. It at one time was the produced gas for coal gas for the city of Ames. It was down the east end of town. It was pretty well dilapidated, and it could have been fixed up, but it was unhandy to go down to the east end laboratories at the west end. Then I found a building on the campus that was considered a temporary building left over from the First World War. And that was being operated, well, it had a garage area that was dirt floor section. Then over in the other end was a popcorn laboratory. Well, they were easily moved out because the garage was for the psychology department, they had some equipment they traveled around over the state with. And it happened that one of the fellows in the administration, Dr. Gaskell, was in on our project. He was the only fellow that knew all the secrets. The president who took care of the money didn't know anything about the project, what it was. He just knew the money end of it. Anyway, Gaskell, being a psychologist, he got the psychology department out of the little building, and we got the popcorn lab out. This building had also been used as a women's gymnasium at one time. They used archery in the open area and so on. Anyway, so we set up this laboratory, or this plant, in the, we call it Little Ankeny. And you see a picture, we added to it, of course. And the two big, see, in the chemistry building, we had only a 15,000 watt induction furnace. Now, induction furnace had to be used because you had to heat in a vacuum. Now, Compton had ordered for the new plant to be set up at Chicago. He'd ordered two 40,000 watt induction furnaces from the Ajax Corporation over at Trenton, New Jersey. Well, as soon as I got time, we got started going. These hadn't been developed, or hadn't been delivered yet, and so they had them delivered direct to Ames. But before they were shipped, I went east. Of course, we needed big vacuum furnace. I visited a company that made big vacuum pumps over at Stokes is the name of the company, over in Olney, I think you call it, division of Philadelphia. So I visited there, and then I went on up to Trenton and met with Spedding up there, and we went out to the Ajax Electrothermic Corporation and talked over them what we might need in the way of induction coils and behaviors of these furnaces and so on. And when they came in October, November, and we soon had them set up. Fortunately, with that $25,000 that Doane gave us, I was not only able to get certain things moving, but I had to get all the machinery. We were going to have to build machinery or build equipment that you couldn't buy. You could buy the power units, and you could buy they'd make the coils for us, but we had to build the units that these things would fit with. We were going to put quartz tubes upside down, quartz envelopes over the build-up charge that we were going to melt, and then we had to have that on a stand, a water-cooled stand, and I had gone down to, we had a company back east supposed to help us on getting this equipment, but they couldn't do very much for us. So I went down to a company down at Marshalltown, 40 miles east of Ames, and discussed, this is the Kiowa Brass it was called then, discussed with their leader what we needed. And he made it one casting, but it leaked, and then we changed the composition to what was called an 85 3/5s. So much copper with 5 zinc, 5 lead, and 5 tin. That worked fine. It made the base that we needed, water-cooled base that we needed for our casting unit, which we would mount on a cart that we could move around. And the quartz tube upside down over that, and then the induction coil, we had it hoisted so we could bring it down over the charge. And with thermocouples, we followed the heating and we'd cast it, and then we'd have a vacuum on it, of course. Then we'd close the vacuum valve and move it over to a pig line where we'd put it back on another vacuum line and let it cool down. Then we'd put another, in the meantime, while I was being melted, we'd bring another charge in. And anyway, that way we first started out with a few silica tubes that were about 9 inches in diameter. Then we wanted to go to a bigger size. We got finally up to 13 inches in diameter. Fortunately, the silica tubes that we had often ordered, well, were always from England. A thermal syndicate over there made fused silica. And fortunately, by the time we got ready for bigger tubes, a company in this country, the Ames company, was making much better grade of silica tubes, and we could then expand to real large operations. Well, so we went on and produced the 1,000 tons. I must explain what the 1,000 tons were. They were in ingots we shipped out. They were 4 1/4 inch diameter, and whatever length we melted up to 30 inches long. But they couldn't handle 30 inches, so we'd saw those in two and ship them out. And the rolling was done elsewhere to roll them out into rods down to the size that they could put in the reactor. Well, anyway, that gets us in our production line. After the war, of course, we continued in action, taking up different kinds of problems. We didn't have to produce uranium. There are many other stories I could talk on, but I better cut off. I should tell you that out here in the exhibits is a little piece of uranium. It's 2 inches in diameter, about 1/4 of an inch high, and that's the cropping from that first ingot, which I saved. By the name of Norman Hilberry gave it to me after.
That's a fascinating story, and thank you very much. I could add a little footnote to that. Based on that same basic process that was developed at Ames at that time, the Atomic Energy Commission went on to build a couple of plants for making uranium metal in large quantities to supply uranium to production reactors, and a couple of those plants in fact supported at one point in time 14 production reactors producing plutonium for weapons. One of those plants is shut down, the other is still operating. It's just outside Cincinnati. It's called the Feed Materials Production Center, and they're turning out in fact several thousand tons per year of uranium metal based on exactly the process we're talking about here, the uranium hexafluoride and the magnesium in a bomb process. So it served us well. Yes, sir.
I might add to that, they recognize it now.
Okay. What the Ames Laboratory is doing now, and we have Dr. Robert Hansen here to talk about that. Dr. Hansen received his PhD in chemistry from the University of Michigan in 1948, and his research has covered many areas of chemistry. He has authored about 124 articles on surface chemistry and related fields. So he's here now to tell us about what Ames is doing at present.
I'm actually going to pick up the story of the Ames Laboratory about where Harley left off. And the first thing I would comment on is that following the production of the uranium, the process for making metallic thorium was developed at the Ames Laboratory, and about 2 million pounds of that was also made at the Ames Laboratory by a process quite similar to the process that was used to make uranium. As Harley mentioned, one of the reasons that Dr. Spedding was selected for initial work on the Manhattan Project was his expertise in the rare earths. And the rare earths were of interest for two reasons. One, that it was believed that the uranium chemistry would be similar to the rare earth or lanthanide series, as indeed proved to be the case. The second one was that the rare earth elements happened to be major fission products in the fission process, and therefore were interesting on that account, because of course the fission process was a new process as far as technology was concerned, and some of these fission products are highly radioactive, could very well have very adverse effects on properties of materials such as metals that could be structural or reactive materials in a power reactor or whatever. Well, it turned out that after the war was over, I should mention that these lanthanide elements, the rare earth elements as one says, constitute a series of 15 elements which differ only in the number of electrons in what is called the 4F shell. And that 4F shell is surrounded by a shell number 5 and shell number 6. So it's really buried. And the consequence of that is that the elements, differing only by inner shell electrons, are extremely similar in their chemistry, and as a matter of fact, for years, essentially defied separation. What happened in the Ames laboratory was that it was found that one could separate these elements by an ion exchange process, and as a matter of fact, this ion exchange process was developed to a technology called displacement chromatography, which made it possible to separate not only the rare earth elements from each other, but to do it with remarkable purity, so that a given rare earth would contain less than 1/100% of the adjoining rare earths, and one was then able to separate these elements in large quantities as their salts. Again, following processes somewhat similar to the uranium process that Harley has spoken about, it was found possible then to reduce all of these rare earth elements to the pure metals in quantities and purities never before realized. That led to some very interesting science because, in particular, it turned out that a major problem in physics and material sciences has to do with the properties of magnets. Why are some elements magnetic? Why are other elements not? With what properties of the elements does the magnetism of the element correlate? Now, everybody knows that iron is magnetic, and everybody knows that cobalt and nickel are magnetic materials. But it turned out, because the electrons involved in the magnetism happen also to be outer shell valence electrons, nobody was ever able to, in a very quantitative way, correlate the electronic structure of the elements with their magnetism. In the rare earth elements, the electrons differ only in a buried shell, and it turned out to be remarkably easy to correlate the magnetism with the electronic structure of the property of the elements. And following up on that, it turned out at the same time, and again as a consequence of the development of nuclear energy, it became possible to do diffraction experiments with neutrons, and that turned out to let you know what was the magnetic ordering of a crystal of a magnetic element. And the consequence of these two things, the availability of the rare earth elements in pure form and the development of neutron diffraction, led to a complete conceptual revolution in the concepts of magnetism. Now, it turns out we still play with this, and let me tell you about something that we play with that is a very current interest, that first came out in some experimental work done in the Ames laboratory, where one was studying the properties of crystals of the rare earth elements as a function of magnetic field implied on them. And lo and behold, it was found that if you took a single crystal of certain rare earth elements that would be something like this, and you put it in a magnetic field, the material expanded in one direction and of course contracted in others. But it did it very fast, and it did it against a powerful external force. In fact, an external force sufficiently strong that was 2/3 of the strength required to make the metal flow plastically, as though you were pushing out silly putty or something like that. Well, that was the discovery, therefore, of what is called the giant magnetostriction effect. And it turns out that in the original material, which happened to be gadolinium, the effect disappeared at 60 degrees below zero, so you were not going to exactly make pie crust cutters out of a material on that basis. Well, years went by, and there was collaborative work between people in the Ames laboratory and people in the Naval Ordnance Laboratory to see if one couldn't find a material that would display this property at room temperature and higher. And indeed, it was found possible to make an intermetallic compound, terbium iron 2, that displayed this property and retained the property to quite high temperatures. Now, what would you do with a material that could do that? Well, it turns out, as is usually the case, the Department of Defense has ideas as to what to do with things that have properties like that. And in this particular case, it turns out that it used to be so, and still is a major way of doing this, that you find submarines by sticking a hydrophone in the water and listening for them, because they tend to be noisy beasties and you can hear them quite a ways away. However, if you are making submarines and you don't want to be found, what do? Well, you try and make your submarine quieter and quieter. That solution has been achieved by both the Russians and the United States. So it's much harder to find them by hydrophones, so therefore it becomes of great interest to have very powerful sonar. And it turns out this material is ideal for a powerful sonar transducer. And so we have found out, because of course, if you work with metals at all, you will know that to make a single crystal of a metal this size, for a lot of metals, would cost you maybe $4,000. And rich as the Defense Department is, they object to paying $4,000 for something this size. And it turns out that we have found out how to beat that problem, and now have found out how to do these material in oriented microcrystals, so the cost has been tremendously reduced, and it now is in the case where we expect to have a commercial plant in operation within a year making this material. Let me tell you about a completely different sort of story on this that is, however, closely associated with it, and it's funny that it is also closely associated with Harley Wilhelm, because it turns out that he was, as he explained, involved in two things when he first joined the staff at Iowa State University. He was involved in metallurgy, and he was involved in spectroscopy. Now, for reasons that I have already alluded to, the business of analyzing for rare earths by conventional chemical methods is extremely difficult. The elements are too similar. You can't precipitate one in the presence of the other. You can't oxidize one in the presence of another, not in most of the cases, and so on. So it became extremely critical, if one was going to develop a good separation process, that one had some other way of analyzing to know whether you were successful or not. And it turned out that the analytical spectroscopy provided an ideal solution to this, and the person who became the laboratory expert on it was trained by Harley Wilhelm and has continued to be a preeminent analytical spectroscopist, and that is Dr. Velmer Fassel of the Ames laboratory. And indeed, it turns out that if you are going to make very pure materials, and that has been an emphasis of the Ames laboratory since its inception, if you want a material, for example, uranium, or a rare earth element, or thorium, and you don't want oxygen in it, because oxygen makes it hard, you do not want oxygen in the feed, or you will get it in the product. And so it turns out that the business of making ultra-pure metals involves the control of the processes through the reactants, through the processing, to the final product. And that is why, in one reason, we have had a major analytical effort in the laboratory, which I'll tell you a little more later on. Some of the things that we're working on very hard, in addition to the terphenol, or the giant magnetostriction material right now, some new efforts have to do with the material's reliability. For example, if you fly in an airplane, you hope that the wings won't fall off, at least not while the plane's in the air. You hope that the jet engine doesn't fly away and fall. That led to the destruction of a DC-10 out of O'Hare Airport a few years ago. And it turns out that the business of establishing that you have reliable materials has to do with the establishment of flaws and how they behave in materials. And we have been developing and have a major effort going on advanced methods of flaw detection, so that principally by ultrasonics, if you had a little hole in a piece of metal, such as the little pipe that Harley was talking about that Compton couldn't find in his uranium, and you wanted to know, is there a hole there? And if so, what kind of a hole? Well, it turns out by ultrasonic scattering, one could characterize this little hole as an ellipsoid. One can establish by the technology that has been developed in our laboratory the axes, the three axes of the ellipsoid, their orientation in space, its location with regard to the external world, and then using the known technology of fracture mechanics, one can tell under service conditions, would this cause the material to fail or would it not? And that's a major problem in technology, very much associated with the safety of reactor containment vessels, the sturdiness of pipelines, and also the reliability of structural materials such as buildings, bridges, and, let's face it, airplane wings. Some of the other things that we're working on very actively right now have to do with the bonding in the solid state. Everybody's familiar with metals, everybody's familiar with polymers and so on, but it turns out that there is developing a bewildering amount of new chemistry with regard to materials in which one has a combination of metal-metal bonds and metal halide bonds and so forth and so on. And these too are turning out to be technologically very, very interesting indeed. For example, many of you may have read of a new permanent magnetic material that has been developed in the General Motors laboratories. The particular material happens to have the formula neodymium-2 iron 14 boron 1. And you ask, what in the world does one need one boron atom in such a gamish as that? Well, it turns out that the boron does a beautiful job of gluing about 10 metal atoms together. So you can imagine a kind of a polygon of metal atoms with right in the middle a little boron atom gluing them all together. It turns out that within the Ames laboratory we have a scientist who has been an international expert on just that sort of gluing together, and his research has led to a major revision of the thinking of bonding in the solid state, and that's Professor John Corbett, who is this year's winner of the American Chemical Society Award in Inorganic Chemistry for this work. We have two other scientists who have received major recognition for work of this sort, Dr. H.F. Franson and Dr. Robert McCarley, so that we have become a major solid-state chemistry effort along those lines. Let me tell you about one or two other things, and then I will cash in on it, which reflects work that we are doing now, and many of the other national laboratories are much involved in too. There has been a national concern about the economic competitiveness of the United States, and there's been a national concern about the following fact. Within the national laboratories and within the basic research efforts funded by institutions such as the National Science Foundation and National Institutes of Health and Department of Energy and so on, there's been much classic and world-class basic research done, and yet that basic research is not being converted to new technology at a satisfactory rate. In fact, it's been a very, very great concern that this basic research has been showing up in new technology in places like Japan and West Germany instead of in the United States. And the consequence of that is that the national laboratories are under the heat, even though that's not part of their original charge, to try and get some of their basic research prepared for transfer of the technology, or rather the development of new technology in industry. So of course we are receiving pressure in this direction, and we're doing our best to do something about it. So let me give you a couple of examples. One of them I've already mentioned, and that is the development of the basic science associated with the giant magnetostriction effect into valuable sonar devices. Another has to do with the business of developing a principle of an analytical method into a useful analytical instrument. I mentioned Dr. Fassel a few minutes ago, and somewhere in the mid-60s, he discovered that, I'll give you a quick basis for the problem. If you put something with table salt in it, a solution of table salt, into a flame, you'll get a yellow color. If you put something with a solution of a strontium chloride instead of sodium chloride into the flame, you'll get a red color, and so on. And you can use these colors to identify what elements have been put into the flame. And as a matter of fact, By using a spectroscope, you can look at a flame that has many elements in it, resolve it into the colors associated with the different elements, and make a quantitative analysis of it. And as I mentioned a while ago, that was one of the things that Harley Wilhelm pioneered at Iowa State. Some of these elements, however, make very strong monoxides, and it's very hard to excite their atomic spectrum. And what Dr. Fassel discovered was that if you can make a flame with no oxygen in it, and you might say, well, wait a minute, how are you going to get a flame with no oxygen in it? That's almost a violation of something or other. No, that's not true. You can take a plasma, and you can get a temperature of 10,000 degrees with a plasma with no oxygen in it at all. And what Dr. Fassel found was that that was a pretty good source for spectra of elements. So he published a few papers. Everybody said, congratulations, Velma, that's very nice. And what are you going to do next? But nobody thought that anything useful was going to come out of that. So what he did was work some more with his students and so on until he found that he could increase the sensitivity, the power of detection of this by a factor of 1,000 to 10,000. And he could also, and this is where you find the people who got money and are interested in developing something, begin to salivate and shed their money and start investing, that he could also determine simultaneously 55 elements in 3 minutes. And he had a gadget that would do this, hooked with a little computer, hairpins and baling wires, a little reminiscent of some of the work you will see in the hall. And at that point, there are now 17 companies all over the world making this, and the income, the gross sales, are $250 million. Unfortunately, Velma did not get a patent on that, and none of that money is flowing into his pocket directly in any event. But that's an example of a kind of a technology transfer where you can't stop with just a basic finding. You have to show that you can do something with it, and at that point, what we always refer to affectionately as the bean counters, namely the industrial executives, are ready to shed money and do something about it. Let me close by making just a few comments on those buildings you see there. The Ames laboratory is a GOCO laboratory, as is Sandia, as is Los Alamos, and so on. But it happens to be located on a university campus, a situation which it shares with Lawrence Berkeley Laboratory, and other than that, it is unique. We operate in much the same way as Lawrence Berkeley Laboratory does. We work to take advantage of this rather than accept it as a handicap. So in both cases, we have a heavy involvement with graduate students, shared faculty, postdoctoral fellows, and so on. And in our case, we are located right on the university campus. The little building to the bottom right of there, and the building across the street from it, which is called Spedding Hall, the building to its left, which is called Wilhelm Hall, I guess you will not be able to guess named after whom, are all government-owned buildings that are part of the Ames Laboratory. Behind Spedding Hall on the right is a chemistry building of Iowa State University, in which the Ames Laboratory rents a good deal of space. Behind Wilhelm Hall on the left is the physics building of Iowa State University, again in which the Ames Laboratory rents a good deal of space and which houses most of our work in solid state physics. We have about 600 people working in the laboratory, about 400 full-time equivalents. We have about 175 graduate students working in the laboratory at any one time. We have about 70 shared faculty members, 25 postdoctoral fellows. We'll turn out about 350 papers in the refereed literature every single year. Since the laboratory's inception, there have been over 2,000 advanced degrees issued by Iowa State University based on research done in the Ames laboratory. The laboratory is very active, as was said in the introductory comments. It is very heavily a basic research laboratory, though we have done our best to couple a basic research with certain applied areas. For example, our analytical expertise is heavily applied in the environmental programs, and many of the very elegant techniques for detecting pollutants in all kinds of environments have been developed in our laboratory. We also have an active support from the Department of Defense in two broad areas, microelectronics and in non-destructive evaluation of materials. More and more, as time goes on, I think that we, as will be the case with all other national laboratories, will be taking an added interest in that kind of intermediate range applied research which assists in the transfer of basic research into industrial use. Thanks a lot.
Thank you both. That was really informative, and I'm sure we all enjoyed it. I'd like to invite everybody to stay and certainly look over the Ames exhibit and also to tour the museum. Thank you for coming.
Yeah. Been in and around that activity for quite some time.